Testing. How's the audio? Here you go. Thank you very much. Well, I'm gonna have a few other coworkers. I'm gonna then do
This should make the green bar go up and down. I don't know if anyone's watching, maybe a couple. Let me know. Let me know if the audio's okay. And this thing should advance. No, I need to click over here. Get rid of this. There's so many steps. Okay. Um, it's a handy little thing. How's the volumes looking? Levels looking good. Okay. Hmm. All right, let's talk about some meta stuff. So I invited you all to a new GitHub group. That is a long-term vision because last time we were like, we should have our own website or something. We should have some way that we control, scheduling. We're going to keep the meetup for now. There's probably going to be a time in the next year when it's like, yes, our homegrown stuff is ready to go. But until then, we're going to keep subscribing. Uh, and yeah, James has re-upped it until December. Then we have to make a decision then. But that's a long way away. So, but if you go to madclj.com, you will see the agenda with my talk and your talk is there. It's right at the top. And it links to the meetup. So that's we have a static site now with no calendar, no nothing, but it's just 2 links. It's good enough. Maybe we can collaborate on that another time. And yes, next week, Eric is practicing his keynote next month, next meeting, yeah, next month, which is the 11th, I think. Yeah. He's practicing his keynote for Heart of Clojure somewhere in Europe. I think you're doing it the week after, right? So we're going to get some cutting edge rehearsal stuff. I've done lots of practice talks. I've officiated a lot of practice talks, moderated. So there'll be a structure. Maybe I'll ask you all to bring a notepad or something, and we'll make sure Eric feels as supported as he can from us. And but yeah. So is this going to work? Yes. So I'm ready. So this talk is not what's on the meeting this month. So I realized that I had this idea that was actually something I don't want users to ever care about. It was a maintainer issue. So what I did was I made a separate repository with so much code that people who are interested in the details, they can go to at the end. This talk is my attempt at really trying to grok a lot of computer science concepts without any code. It's one of those. It's a challenge for me, and I hope I get something across. But my main intention is sort of inspiration. Like, wow, I want to go tinker with that. Whatever made that image, you know. Uh, but it is related to Malli, uh, and but it's got a lot of programming language theory, a lot of computer science theory in it, but you wouldn't know it. Um, I'm going to try and uh, have intuitive uh, explanations of all the things that I talk about. So this is really for a general audience. I'm not expecting programming. I'm expecting that you have followed a cookbook, like you know what a recipe is. Or, well, there's a particular vegetable that this entire talk is about. Okay, so the shape of self-referential computation. I don't know if that's a real thing, self-referential computation, but to um, I'm going to say that everyone has an intuition for what this is if we work backwards from things that you already know. So if you think about following a recipe to create to cook a meal, there's going to imagine you have a piece of paper with 10 steps, and you have the recipe in front of you, and you decide I'm going to cook. So what do? You go to step one, I don't know, boil the water. So you boil the water, and then what do you do next? Well, you go to step two, which the thing you do is then follow a recipe. So notice you're following a recipe and then following another recipe. So it's almost as if you could rip off the first step and, well, what have you got? You've got a recipe. So the same thing that you do to follow a recipe, if you if you keep doing it, you will eventually follow the entire recipe. So that the self-referential phrase there um, points to the fact that the next step is to follow a recipe. Oh, we're already doing that. So it's this interesting folding in on itself. I can very succinctly tell you how to follow a recipe, and it will work for all recipes. So very interesting idea. And if you're very diligent and follow to-do lists from top to bottom, similar thing. It's ideally, this is, you can cross off the top of the to-do list. What have you got? You've got a to-do list. Well, you know how to complete a to-do list. Do the same thing that you did before. So this idea of self-reference is fundamental to computer science. It's there's a lot of it's very important that computers be able to represent these kinds of problems and then be able to do something once they are represented with them. So, for example, a recipe, a computer should be able to make a recipe and then follow it. Okay. Okay, this entire talk is about onions. This entire talk is about onions because I think it's a bit of a stretch to say a recipe contains a recipe because well, it kind of, but I don't think it's too much of a stretch. If you take off a few layers of an onion, you've just got an onion, right? So I think it's a pretty compelling self-referential object that um, that later in the talk we're going to compute. We're going to perform computations that about this onion, this self-referential object. And for the purposes of this talk, there's nothing more important than processing onions. Okay, so this is a Clojure meetup. So Clojure is an interface to a computer, so we want to represent onions in Clojure. And you don't really need to know what these square braces mean. But all you need to know is that if there's one on the left, there's one on the right. They're always matching. And you can kind of see the onion if in your head you start drawing circles. So here's the core, right? That's pretty much touching. But if you draw a circle, there's the next layer. Keep going and going and going. There's probably 5 or 6 layers here. So I've boosted the font size here. But this on the next slide, I will flatten everything out, but it's still going to be an onion. So a Clojure onion is going to, this first one is an onion core. The second one, well, we add a layer, which is a core with a layer around it. And you can keep going, and there should actually be dots down here. And this is a core with 1, 2, 3, 4, 5 layers. And again, think layers and also when you think about layers, think about the fact that you can take them off and you've still got an onion underneath it. You can put one on and what you've got is another onion. Okay, again, for the purposes of this talk, because onions are so important, and I promised to do a talk on Malli, there are 2 very important operations on two very important operations to do with onions. One is called validation, which is the computer, given an onion, should be able to tell us whether this is an onion or not. Give us a yes or no answer. And the other one is a generation. We should be able to make a valid onion if we ask for one. So first off, if we were to teach a computer how to generate, if we teach a computer how to validate an onion, which again is teaching the computer to be able to answer the question, is this an onion? Well, one way to do this would be to think of all the different ways an onion can be created. And then, for example, the smallest onion, well, this is an onion if it's a core. Okay, but okay, there is a bigger onion than that. So, okay, well, this is an onion if it's a layer with a core inside, which is this one. Well, there's a bigger one too. It's a layer with a layer and a core inside, and a layer, 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 core. So there's dot, dot, dot. You can see that this isn't sufficient to describe all onions. Well, sort of. We'll see later on. It could be. But one way to see this problem is that this is a self-referential computation. Yeah, this part I'm still grokking. That how can you go from this to a self-referential computation? But maybe I'll figure out how to explain it another time. But it's actually quite simple. How to check if something is an onion. Well, you check this is an onion if this should say either it's a core or it's a layer with an onion inside of it. So if you think of an onion with 3 layers, it's an onion because it's a layer with an onion inside of it, with another layer with another onion inside of it. I think one more, and then there's a core inside. So this will check if this will tell you if something is an onion or not reliably. It'll always recognize an onion, no matter how big it is. Okay, remember the other important operation for the purposes of this talk is called generation, where the computer can make you an onion on command. And if we were to teach a computer how to do that, we might start off with something like this. An onion can be created by creating a core. So that's the smallest one. It can also be created by creating a core with a layer outside of it. And you could also create an onion with a core with a layer and another layer outside of it, or a layer and a layer and a layer. Now, there's something subtle going on here, because if we think about validation, notice that it was natural to talk about the core being inside, and the way I wrote it, the core, we're now putting things outside of it. So it's like we're building it up. I don't quite know what that means yet, but it's kind of interesting. But if we think about how to make this a self-referential computation, here's the recipe, the algorithm. So an onion can be created by creating a core or creating an onion with a layer outside of it. And how do we create an onion? Well, there it is. So this will create as big an onion as really the computer feels like. Okay, so one of the things I want to, one of the big questions I want to answer is, can you automatically create these computations given the description of an onion, which we saw with the, if you know something just has a bunch of layers, can you automatically know how to validate or generate it? And this is an idea that's fundamental to the design of several libraries in Clojure, Schema, Malli, and Spec. And their insight is that if you create a specification of an onion in a way that a computer can understand, then you can automatically get these other functions. I haven't used that word yet. these other, yeah, I don't have a better word. So how might you specify an onion? Well, it sort of looks similar to uh, the, the slides before, the validators and the generators. An onion, well, it's a core, or an onion is a layer with a core inside. An onion is a layer uh, with a layer and a core inside, and it goes so on and so on. And the self-referential specification is an onion is either a core or a layer with an onion inside. And this looks almost identical to the validator. So you can imagine how going from this to the validator would, it could be something that a computer could do without any intervention. And also it looks similar to the generator where we were building it up. And yeah, those libraries use that insight that you can start from teaching the computer what an onion looks like, and then it can give you all these useful things to do with the onion. Okay, so in this talk, again, we are asking, can we automatically create validators and generators from onion specifications? Yes, from the specification of an onion, we can create an onion validator. This is something that's not novel. This is what Spec and Schema and Malli do. What I'm going to concentrate on this talk, we're going to talk about validators, and we're going to learn how validators are currently created in Malli, and different ways of creating validators. We're going to touch on a broad range of programming language topics, but we're going to do it via, well, pretty pitches, but they're going to be keynote, drag and dropped in the last minute pitches. But this is the part that I don't know, that activated my brain, that everything has its own computation, has its own shape, and a lot of different topics in PL change the shape of the computation. I hope to leave you with an intuition about what that means. Okay, so we're going to talk about validators, which in this case, how do we know if something is an onion or not? And from here on, we're just going to show a bunch of shapes, give them names, and then give them pointers to computer science concepts. And there'll be code at the end, as in like after the talk, for you all to look at if you are impressed by the pictures. Okay, onions. So the first, if I told you that you had to sit down and check whether this thing is an onion, you might do something like this, which is you have the specification on the left, which is an onion is either a core or a layer with an onion inside. And then you have the onion on your right. And you look to your left and say, well, what do I need to understand about the specification first? Well, it's either a core or a layer. Okay, well, I'll remember that. So on my right hand, I'm going to look for a core or a layer. Okay, well, I found it. And this analogy of this is braining and this is looking, we're interpreting what this means with our noggins. And then, let's see, we've checked that the outside is a layer here. So we're going to move on to the next layer. And I think, and then skip a bunch of slides, do the same thing again and again and again. And in the middle, it's going to be a core. So this kind of computation is called an interpreter in programming languages. And it has this triangle shape. That's a lot of symbols. I wish I had put half as many there. It should have, okay. Remember these symbols of thinking and looking. So thinking was, well, what does the specification want me to do? And then looking was, well, where am I at in the onion? So it's a triangle here because as we go further into the onion, where well, that's the intuition here. It's going further into the onion, so therefore it's going further down the triangle. But you can see we're sort of getting uh, getting rid of layers as we go down. I guess so. I didn't even think about that. Yes. Now the question is, what is this? I don't quite know the best way to explain this, but one way to think about it is we've got to check our work to make sure that we've done the right thing, and then all the way out until we have the entire onion again. And this isn't really something, it's sort of implicit. In that example with our hands, we're not thinking, well, let's make sure we check our work on the way out. But computers have to do that to make sure that everything is in order, basically. It's like, yeah, it's checking its work. Whew. Okay, so I didn't just I didn't say it was a triangle. What I did was I built a program that simulated this idea of checking the specification where we're at and then checking the onion. And when I ran the program, it looked like this. You don't need to understand what this is. It is a triangle, and you can see that it's a triangle. But okay, what could we do better here? Well, if we check a different onion, we're going to have to keep checking the specification, right? I think I have a good diagram next. Okay, yeah. We're checking two onions here, and we're thinking twice as much. You know, if I told you to check two onions, you would either build a muscle memory or some sort of short-term memory about, oh, I know what an onion is. I can check 100 of them. But on maybe the 10th one, you might even put that specification to one side and be like, well, I know I need to just check for layers, right? And let's see if we can apply that concept to validators. So the idea would be we do all the thinking up front. So say I tasked you to check if this is an onion, well, I would give you 10 minutes to really internalize that specification, maybe give you a dummy onion that doesn't smell, give you, give you some reps, yeah. But notice once you've internalized onions, you can harvest, you can process onions without having to think about what's the specification. And you can keep going and going. It's unfortunate that there's the same amount of brains here, but you can see this would quickly be less brain power. Yeah, maybe this is a good analogy. It takes you twice as much energy to practice, but you will reap those returns on the 10th onion, the 100th onion, to a very large degree. Okay. So the trick here is that the computer needs to learn ahead of time how to check any onion. And remember, an onion can be infinitely big. So how is a computer going to remember how to check an infinitely big object? Well, if you get it wrong, we're going to get what I call a funnel, which the computer's This is a consequence of the computer not realizing that onions are self-referential, because we learn that a core is an onion, a one-layered thing, a two-layered thing, blah, 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 blah. And the computer's missing a bit of insight. That's sort of the crux of this talk. How do I, remember we're automatically, from the description of an onion, we're supposed to learn all of these subtle ideas, like the onion is in fact infinite, and we shouldn't try and imagine how to check all onions, like literally, in this sense, because computers can only hold, even with an infinite amount of time, you would never be able to prepare enough if you use this strategy. Remember the strategy of the sort of obviously flawed approach of just listing all of the approaches? It's very similar to this. Okay, so at this point, there are a couple of ways you can go about this. And first off, I'm going to show you how Malli currently deals with this problem. Then I'm going to show you something that might be a little cleaner, a little different, that might have a little better experience for users, and I'm excited about. There you go. All right, so this is actually part of the code, the GitHub thing I'm going to show at the end. This is what the funnel looks like. It's literally a funnel. Not literally, but you can see that this says compile. And it's because this idea, let's go back a couple, this idea of preparing ahead of time and then reaping the benefits later, this is what a compiler does in programming languages. So the problem is we're compiling, or trying to prepare for being able to check if something's an onion or not. But we don't know when to stop. Yeah, so the first solution I'm going to show is Malli's current approach, and then another solution called tying the knot, which I actually don't know if I have a great explanation for that, but we'll get to that. Remember this slide? This was, and in fact, I just told you that this was flawed. This is a problem because we don't have, if I was writing this out, there's not enough time in the universe to be able to write all this out. There's a problem here, but there's a key insight, which is computers can only represent finite onions. So that means we only need to know how to check an onion up to a finite number. We don't actually need to count forever. We only need to know how to do this for the biggest onion the computer sees. So yeah, there's a couple of concepts here which I actually didn't think about. One is called laziness. And if you think about it, it's sort of lazy to only know how to create the biggest onion that you see that particular day, because maybe another day you might need to know more. But it's sort of lazy in a good way, like, because you're not doing more work than you need to when you prepare, say. If you need to, on day one, you see an onion of layer 10, you need to write 10 of these statements. From day 2, you see one of layer with 20 layers. On that day, you can do that preparation. So that's the concept here is called laziness. And there's another concept here called memoization. Remember the thing I just said with 10 layers and then day 2 another 10? Well, you don't actually have to relearn what the first 10 was. You can remember. If on day 2 you need to learn 20, you can remember how you validated the first 10 layers. So this is pretty much how Malli works right now. It's lazy and it's memoized. So it's lazy as in it doesn't need to compile the entire, um, compile all of the ways or prepare all of the ways that you can check if something's an onion. It's memoized because it takes advantage of previous results. And there's a third thing. Yes, this requires your intervention. You need to tell Malli when to be lazy. So going back to this idea of self-reference, whenever you're at a point, currently in Malli, if you create an onion, you have to say, at what point do we tie the knot? If you think about like a piece of string going, do I have the, all right, let me just find boo. Okay, okay. If you think of a piece of string tracing where you go, we get to onion, well, it's back here, and imagine tying a neat little bow. This is tying the knot. Tying the knot. Yes, okay. So you need to tell the library when to tie the knot, which is kind of annoying. Kind of annoying, and also you might not know, you might forget. Say if it's a more complicated, well, there's nothing else exists but onions. But if you think about a red onion, sort of has a white layer and then a red layer, and then a white layer and then a red layer. That's kind of odd. That's a little more complicated than a white onion. You might mess up exactly where the knot is tied. Well, where is the knot tied if you have a white layer then a red layer? It's somewhere, but you have to know if you use Malli today. And there is this interesting shape, which I'm calling a Christmas tree shape. And if you think about, because it's lazy, we only compile the validator up to the point that we currently need it to. So at the top here, we prepare a validator because we know we need to inspect at least one layer. You can kind of think of the indentation back as so you've done your homework here for one layer, and you've just sort of gathered your notes and you're ready. You're a bit you've internalized how to do one layer. So now you're ready to go to a different task. So that's going to use a different part of your brain. You don't have to remember in the interpreter, you had to keep both things in your head at all times. That's sort of what's happening here. The two things are separate. The reading the spec and checking the onion. I sort of made that up on the fly, but maybe there's a bit more to it. I mean, obviously not maybe. There is definitely more to this. But here's the pretty picture. Actually, I forgot about, this is actually a Christmas tree with a star on top or a triangle on top because, or maybe it's not, but we'll see. There is an extra bit here Is it extra? Maybe this isn't fundamental to this picture, but there is a little bit extra here, which is maybe you have to prepare a little bit extra to know, okay, we're talking about onions today. We are talking about onions. So there's a brain at the very top here. No, that's not the right thing. There should be a star at the top, which is a little bit of extra preparation. But I don't think that's really fundamental to this picture. What's happening here is where this says compile and then run, which is looking and checking, and then compile and looking. And remember, I said this was memoized. So the next time an onion is checked, you actually don't need to compile because you remembered, well, you already knew how to check that kind of onion. So actually the next time you use this validator, I should have included this picture, but the shape is going to be different. It's probably going to look more like a triangle because you've done all the work of interpreting or compiling the validator in advance. Yeah, there's probably a bit more subtlety there, but I'll leave that to the end of the talk. Okay, going back, remember, this was the problem. We needed a way for the computer to know that onions were infinite. You can't possibly prepare for all onions. Well, kind of, using the naive approach. And that remember, this was Malli's solution to that. Well, how about you just tell me when to stop? And there are some other ways for via laziness and memoization for this to actually work in practice, for people to not think, oh, this is so slow, this takes the computer so long. It actually only takes extra time the first time because we remember how to compile the validator. But this was the picture I showed you first up, which was do your homework, realize that the onion specification is only 3 lines long. You don't need to be lazy or memorize, or you can just be proactive, be eager, and actually realize, oh, this is a small, understandable object that happens to be infinite, but it doesn't mean we have to prepare infinitely. And we can do it in such a way that when we check if something's an onion, we don't need to go back ever. So this sounds much better than obviously this, and it's different from the interpreter. I'll say that to the end of the talk because I juxtaposed them all. And so this requires that we tie the knot automatically. So you give Malli here the definition of an onion. Malli will say, oh, okay, that when you say onion, we've already seen onion before. So we need to tie this knot. Well, okay. This is the trick. You need to know when to tie the knot, and you need to describe to Malli how to tie the knot for things that look like onions. And actually, this was the motivation for my entire talk. There is a trick, and I'm not going to talk to you about it because it would involve me putting a object that's so convoluted that everyone will go to sleep. So I realized that only me and Tommy, who's the creator of Malli, and other Malli maintainers need to care about the trick. But you can ask me about it later, and it might be in the code. Yeah, I called this a capital B shape, but I think it's, oh, I already used the, just sort of like a triangle wave shape. Toblerone, yeah. Okay, good, because I've already used triangle wave later. Well, no, but the problem is, remember, okay, part of the advantage of this is that you can process any number of onions without paying this penalty. So I want to get that intuition across. And I think, unfortunately, capital B is not, doesn't give that essence. But it's going to look like a capital B if you just say, please check this onion from scratch. The first the first triangle is going to be the compilation step. And there is some magic so that Malli will know that we need to tie the knot. And it's essentially, have we seen this before? Have we seen this before? Yes, we are currently inside of onion. An onion is a layer with an onion inside of it. Well, we're already trying to figure out what an onion is, so it must be time to tie the knot. And notice we only need to compile a couple of steps. I think this is like a 7 or 8 or 9 layer onion, but we only needed to compile a couple of layers. And if I were to separate this part, I would be able to reuse it to have a nice, to not have to compile this again without using technical words like laziness or memorization. This is just you doing your homework, getting muscle memory, getting it in your short-term memory, and then executing your job, which is to check if something is an onion, and you've internalized what it is. All right, so there's a couple of bonus shapes in the few minutes I've got left. Imagine, remember this analogy here, this sort of approach of checking whether something's an onion. This is called an interpreter, where you're checking where you are in the specification and then making sure that the layer matches up with the specification. So you're sort of doing two things at once. It can be a lot. But let's say you're okay with doing that. It's just that you need a little break in between each layer. So imagine if you had a logbook where you could say, well, I'm at this line in the specification, and I'm at this layer. And then once you write that down, you can go take a cup of have a cup of tea, rejuvenate, put that aside, and come back with new, renewed energy. And using this approach, you should be able to check an onion, that's 10,000 layers deep, given enough time, because you will always have enough energy, you will not be overtaxing yourself. So, okay, this looks way more technical than it is, but this is like the interpreter. This is checking one onion. So first we see, well, where in the specification are we? Okay, we're here, and then where in the onion? We're here. Okay, well, okay, now I need a break. Let's write down where we're at, take a break. And this represents the computer doing the same thing. It does the equivalent of writing down where it's at, so it doesn't need to remember that where exactly in the onion it is. And then we do that again and again. And if you the computer is doing more work in a way, or it's using more of its memory, the bigger this triangle is. So it's actually, in the same way that you could process a 10,000 layer onion, a computer could really process any finite shaped, any finite sized onion given enough time, because we're not overly taxing the computer. We're not asking too much of the computer here. So this is called a trampolined, that should say trampolined interpreter. It has this not sine wave, the other one, triangle wave uh, pattern to it. And it looks flat, even though what's actually happening is basically the same as checking the various layers of the onion. But notice the computer, like there's numbers on the left here that basically tell tell you how hard the computer is working in terms of remembering things. These are all 0, 1, 2, 0, 1, 2. Before it was, well, if you have a 15 layer thing, it'll go up to 15. And we can also apply this to a compiler. We can, in advance, have a prepare for a, I don't know if this has a physical analogy though, in terms of asking you to prepare. But okay, let's just say the computer knows how to prepare in a way such that it can check any number of onions without having to check as it goes. So the previous one had brains here, you know, it had the thinking. This one's called a trampolining compiler, and it looks sort of like a P shape. We do some work here, which is actually a couple of layers deep because it takes until you realize, oh, we're tying the knot. So this is compiling, so we're preparing the validator. And then actually this is just 1, 1, 1, 1, 1. We're just checking each layer, and we're not doing any thinking at all. All right, so I showed an interpreter, which is thinking and looking at the same time, which was this sort of taxing idea of remembering where you are in the specification and where you are in the onion. I showed you how Malli deals with not knowing how to tie the knot. But by having a lazy approach, of which you have to tell it when to be lazy, it's also memoized. Showed you how to tie the knot. Sorry. I showed you a compiler that depended on having to tie the knot, which is Toblerone. So yeah, triangle, Christmas tree, Toblerone. We have our trampolining interpreter, which is the triangle wave, and this one was the P structure. So that's cool. So here's the code, Malli model. It'll be at the end of the talk, which is now. And here are the different shapes. So you can see the triangle, Christmas tree, Toblerone. This was the triangle wave. And here's the P. All right, that's it. All right. Yeah, go.
So does this mean that I would write a recursive Malli spec or schema, and I don't have to write a ref in it?
So the question is, does this mean if I can write a recursive Malli specification and not have to write ref? That is basically my idea.
Okay.
Yes. And there's a working prototype here. And it's how, let's go back to the pretty pictures. Oh, yeah, this one's good. These things here, I didn't really know how to do them with refs, I think. It was more intuitive to figure out how to tie the knot and then build. Is that true? Because this is memoized and yeah, I think I stand by that. I don't know. I couldn't explain to you right now how to do it. There is, I didn't use the word scope in this talk, and that's the sort of the one trick that I need to keep in my head while doing things, because the public service announcement that I want to get across is that Malli uses dynamic scope. And you only need to care about that if you're a Malli user. But Malli, if you think about using Malli, think about binding, not let. Like forget about threads, like single thread binding. think about binding, not let. Whenever you make a registry, binding, not let. In other words, using computer science, programming language, it's dynamic scope instead of lexical scope. And this is something the dynamic scope makes. So I didn't talk about generators at all. What got me interested in this area was I spent a couple of years figuring out how to tie the knot in the generator namespace of Malli. So for people who are familiar, there is a generator called recursive gen, and somehow we need to know how to make, to turn the specification of an onion, say, into a recursive gen. It's non-trivial and complicated by the fact that Malli uses dynamic scope. And my thought was then, oh, we have to do this for validators and explainers, and like there's a lot of other operations. And I got very scared. Like we should just get rid of dynamic scope. I think I'm not there. I think there's a backwards compatible way of doing it. I haven't figured it out. But I guess another relevant detail is I just got commit rights to Malli because thank you. That's probably one of the coolest things to ever happen to me. And one of the reasons was to qualify for Clojure's Together funding. But the other reason was that I'm the #2 contributor in the last 3 or 4 years. And part of it is trying to figure out these problems. And I'm not going to work on this in particular because I haven't actually, I'm not saying I've solved this because honestly, I have not. Like this, there's a good reason why it uses dynamic scope because lexical scope is it's much harder to implement. It's much harder to think about. Maybe I'll come back next time with how to implement lexical scope in something like Malli.
My only experience with non-lexical scope is Emacs lexical.
Yes.
Which, inside of Emacs.
Yes. So you should have that same feeling about your Malli registry.
Okay.
Who knows? So I think that Malli registries have to contain a qualified keyword as a short-term to lessen the risk that you will encounter the problems of dynamic scope. There's a caveat though, which is the initial registry, because when you write a namespace local registry, you're going to do it in the same namespace. So all your qualified keywords are in the same namespace. So it starts to give me alarm bells. Like, how many people actually have used dynamic scope without knowing it? Like thinking, oh, this is let. It's as if, as I said, like it's binding, not let. It's like confusing binding with let. It's gonna, it may not bite you, but if it does, good luck. Yeah. Yeah. All right. Eric, you got anything?
So I've never used Malli. So when you say stay away from because
What was the last part?
would you say stay away from Malli because of that?
Oh, so Eric's asking, he says he admits that he's never used Malli. It looks like it's getting popular. Is this a reason to avoid Malli? I think this may be my pedantry coming across, where I like to know that my abstractions are 100% sealed. Okay, I like to have my abstractions to not have intentional holes put in them. And this is an intentional hole. So the question is this a reason to avoid Malli? I don't know if anyone's ever written. Okay, I polled the Malli Slack, and my coworker Kirill told me that he knew that it was dynamic scope, and he once used it intentionally. And when I asked him, it turned out that he had this ingenious way of encoding lexical scope using dynamic scope that totally freaked me out. To give you a bit more information, he was compiling TypeScript types into Malli. TypeScript types have interfaces with arguments. They're lexically scoped, but you can't do that in Malli. So what he did instead was have, so it was an interface of foo that takes an A. He would make a foo and then bind a variable A to some impossible thing. And then whenever he'd call foo, he'd need to remember to bind A as well.
So you make a new thing,
Yes,
a unique thing for that one.
that's the thing. It works perfectly if it's unique. That's the thing. But these registries are mutually recursive. They go across namespaces. It gives me the heebie-jeebies, you know?
Just the name of the registries, if I'm just depping out schemas,
Yep.
I don't have to worry about dynamic scope at all.
So if you just use it like spec in that you have one initial registry, it's basically like global scope, you know? This is another feature called local registries, where you can say, this schema has a name called onion. So I think actually to put onion into your registry, you would have to say something like, an onion is, no, actually you could get away with that. Okay, I think mutual recursive, okay, hang on. So yeah, if you don't use local registries, you're fine, you're basically in spec land. But if you do use local registries, then they use dynamic scope, and local registries are quite handy for things like mutual recursion. So for example, if you wanted to say a red onion is either a red layer or that has a white layer inside of it, or a white layer that has a red layer inside of it, you don't want red layer and white layer to be accessible. You just want red onion to be accessible. So you'd say a red onion is private, please. You know, that's when you'd use a local registry to encapsulate some names. And you can use lexical scope to do that, like let fun, for example. No, the schemas are. Sorry, all of the above. But once you introduce local registries, you start having dynamic scope problems. It's like, if you don't have local registries, it's mutually recursive, but you're using global scope. Everything's stable. You're not redefining what an onion means or a red onion. But once you try and figure out what a red onion means, you are using dynamic scope to figure out the layers where you're at. Yeah.
Say that the example of potatoes really goes through the difference of being convoluted, right? Like, were you saying that the example of how you would get bitten by dynamic scope is convoluted? And does
Yeah.
that speak to, like, for most people, you don't actively have to worry about being bitten by this?
Yes. The example that I gave that Kirill was trying to encode lexical scope using dynamic scope, that's basically the example. You know, it's, but I guess I'm worried that someone might accidentally do it. I'm even more worried if someone would intentionally do it. So, but I don't think it would be something that's you could imagine maybe a linter rule or two might take care of the whole problem. Or maybe a little extension, a warning maybe, when dynamic scope is triggered. No, because you would need an alternative like lexical scope. And that's work in progress. So Eric's question is, what is the dynamic scope used for and why does it exist at all? It's used to construct schemas that are complex, that may have private internals that are mutually recursive, or maybe like something like hiccup has different ways of being constructed. You would say a hiccup thing is either, I can't remember what it is, like a vector of this and a map of that, and maybe a symbol here or there, and you can do that. You don't want all these details to be public. So you would make a sort of letrec-like thing, which in Malli's case means you're in dynamic scope land. It does change. It just happens to change to the same thing over and over. So that's what an implementer needs to make sure. If you tie the knot, is the onion that you saw last time the same thing as you saw? No, I'm talking about the schema. Yeah. If you tie the knot wrong, then you've compiled the function wrong. Yeah. And I think one of the insights so there was a couple of insights for me, which was the way you know you're going back is that the onion is the same as last time you saw, but also the dynamic environment. So the pair is the same. It's the environment and the onion itself. And there are some ways where you could see the same looking onion again, but actually you have to unfold it a couple of times before you see the same thing again. And this was actually a bug that I had in the generators. That's why it took me about 2 or 3 years to implement, because I kept finding these issues. We'll do one more question.
I just want to understanding within the scope. So I was thinking about is this happening in that schema that is referred to straight in that schema? So you can like going down sort of personally and also street. Is that the case?
So you want to know when the dynamic scope happens. You're reading the Malli README. Yeah. So
it's not doing anything fancy with the registry, so I don't quite understand
yeah.
functionality specifically.
So when you write a keyword in Malli, if it's not surrounded by a vector, it means a reference. And what that means is, what does this name mean right now in the registry? And if you don't have any dynamic scope going on, the registry will just be a static thing that is like global. It's a global thing, like Clojure defs, where you don't use any binding statements. The problem comes when you start needing more intricate schemas like hiccup, or maybe even an onion or some mutually recursive thing. Now suddenly, as Malli is interpreting the schema, it's having to redefine what the names are. So when it sees an onion as this, and it goes to the layer case, and then it sees onion again, it looks it up again, and then when it looks it up again, the very first thing it needs to do is remember, because it says an onion is this, so now you have to add that to the environment again, which happens to be the same thing.
So it's sort of referring to names thing, and each time it's referring to a name.
Yeah.
Something like that time, that is changing.
Yes. In an analogy to spec, imagine if spec had a way to dynamically redefine a particular name in the registry, like as a spec. The spec is the body, but with this extra name being redefined as something else.
So like Clojure has plenty of scope.
Yeah.
But it's still have to mark
Yep.
And so it often feels kind of safe, right? It's like, one or two things that put earmuffs on, and like, I know to watch out. Is something like that possible in Malli, where you only define certain names, and so it would feel safer because you know that they're different marks. It's weird.
Yeah. Okay. So Eric's asking, well, he's making the point that Clojure has a way to actually shield us from sort of, yeah, the perils of dynamic scope, I think is the meme or whatever it is, the saying, by having to opt in. Like by default, things aren't dynamically scoped in Clojure. You have to actually ask it to be dynamically scoped. And Eric's asking, could Malli have something like this? It's very similar. It's very related to what I'm thinking about right now, because I'm basically thinking, would you be able to change Malli's scoping rules? If I decided to go from dynamic to static, would that break anything? And I think, like using your analogy, if making dynamic scope opt in, would that break anything? I don't know. And but there's no way to say like, don't make this dynamically scoped. It's a very simple thing where you just add it to the registry. There's like, if you check out this, these are all 10, 15 lines long. They only support 2 schemas, and they are 10 to 15 lines because I wanted pretty names here, but they really should be more like 6 or 7. And they have a syntax at the top. Forgot what they're called, with the colons and the equals.
So,
Yeah.
you know, I think maybe this is an interesting thing. Based on like in Scheme, they do macros, right? But they do hygienic.
Yep.
There's this whole like separable gets involved with the first, and it's created like this. I call it a cottage industry of research, like who's hygienic macro, maybe that is actually.
Yep.
Whereas in Clojure, the way we get around it being is to have a few little constructs like the auto widgets and stuff like that, so that you're not rebinding something that's larger scope. And to me, like it's much more comfortable that hygienic macro and it avoids a lot of problems that hygienic macro aims to solve. But you probably could do some damage if you wanted to. And so I'm just wondering if, like, instead of trying to find a way to make it perfectly safe, you just make it like super easy to get it right.
Yeah. Okay. So Eric makes a great point, which is that Scheme has arguably a perfect macro system. It has this property, it's hygienic. And Clojure is more utilitarian. There's actually a couple of little points we need to be careful, but as long as you follow the rules, you will, in practice, be about as good as a Scheme macro. Unless you start doing things like macro writing macros, then you're on your own. And one of those tricks is to make sure that names that are local are always unique, and you put a hash at the end. And you're saying that couldn't Malli have a similar attitude? Could we have an easy way to get it right to avoid the perils of dynamic scope? I think that actually seems to fix 50% of my beef, which is that different schemes, different specifications can refer to the same thing. You could, I mean, schemas are just data. You could do a gensim. You could say, let the red, let a red onion be gensim red layer, and then always use the same gensim, right? You still need to be, so that would still, Kirill's example of hacking A to mean something else, that would still be a problem, but I think that eliminates the other problem of different schemas using the same names, and in a way that's kind of the scarier problem.
Does this mean like, in this context, name means string, and then this other context, name means new, or something like that?
Yeah. Yeah.
You don't know which one you're gonna get, because you're referring to the same name.
Yeah. Yeah. So the question was, is this like saying a name is a string and then a name is a UUID? Like, have we redefined what this name means? And the answer is yes. It's not a stable reference. This name isn't stable. It's mutating. It's changing what it means, which is useful, but maybe too powerful for say describing onions. Or most things that we want to describe. All right, I'm going to stop the stream. Actually, I'll just check if anyone. All right, well, I know the audio is good. Thanks, Ben. All right, I'm going to stop the stream. Thank you.